So remember what we're trying to do when using a t-statistic or a t-test. We are trying to test hypothesis about a single population parameter. Okay, so here let's say we want to test, this is a more generic way of writing things. So we want to test the effect of, what is the effect of xj on y, and that is captured by beta j, right? So this is a population parameter. We don't know what this might be, so we are trying to hypothesize what this is in the population. So we set up the null hypothesis, which says that there is no effect, right? There is no effect of xj on y, right? This is how this null hypothesis is set up. Beta j equals 0, and the t-statistic, like we defined in the previous video, is basically defined as how far is our estimate beta hat j, right? So this hat is representing that we've estimated the model. How far is this from the hypothesized value beta j, which is 0, right? So this goes away, and this is because this is just 0. Otherwise, there would be a value here, whatever you're hypothesizing. In this case, this is just 0. But how far is beta hat j from 0, or the hypothesized value, relative to its standard error? Okay, so that's what this t-statistic is. Okay, and we said that we can look up the t-distribution for the various degrees of freedom and try to understand whether we should reject the null hypothesis or fail to reject the null hypothesis. Okay, so we'll get into that language later, but right now the important thing to note is that the standard error will always be greater than 0, and so the t-statistic will have the same sign as beta hat j. So whatever you estimate beta hat j to be, whether if it's negative, then the t-statistic will be negative. If beta hat j is positive, then the t-statistic will also be positive. Okay. Now, since we have set up our null hypothesis and we are clear on what that is, we also need to have an alternative hypothesis. So what are we testing it against? Because this is a test, we need to have the null and we need to have an alternative hypothesis. So this is set up in different ways, which we'll see. So if we were thinking about one-sided alternatives, so in which case if our null hypothesis, let's say, looks like this, if we hypothesize that beta j is less than or equal to 0, then we can set up our alternative, which is represented by h1 or sometimes ha, right? So either you use ha or you use h1, it's the same thing. Here we are saying if this is our null, then the opposite is our alternative, right? It's the complete opposite of that. And this is a one-sided alternative, right? So this is not remaining agnostic to what we are hypothesizing in the population. So we're saying this is a positive, or it could be negative. It really depends on how we set it up, okay? So I'm going to walk you through a traditional approach to hypothesis testing, okay? And essentially what we're doing is we are trying to ask the question, how big does the t-statistic have to be before we reject our null hypothesis? Or in other words, that we conclude that the null hypothesis is very unlikely. Okay, so let's think about the various steps for hypothesis testing. So the first step is you choose the null hypothesis. You set it up. Okay, so we can have a null hypothesis which is hypothesizing that beta j is equal to 0. We're remaining agnostic to the sign of beta j, whether it's positive or negative, right? Or we could have a one-sided alternative, which is to say that beta j is less than or equal to 0. right? So either we set it up this way or we set it up this way. So this is called a two-sided, and this is called a one-sided test. Typically, a two-sided test is used because this is more generic. This is allowing for the possibility that xj has no effect on y, but this one-sided test is basically saying that xj has a negative or no effect on y. Okay, so whatever the null hypothesis, once you have set it up, the next step would be to choose the alternative hypothesis. Okay, so the alternative hypothesis in a two-sided case, let me use a different color here. So if we were talking about a two-sided hypothesis, the alternative would be that beta j is not equal to 0. But under a one-sided alternative, that would be beta j is greater than 0, right? So depending on what the null is, we are writing the complete opposite here. So this is our null, this is the complete opposite of that, okay? And so we can choose an alternative hypothesis. So remember the first two steps: choose a null hypothesis and then choose an alternative hypothesis, okay? And these are related. These are just opposites of each other, okay? The third step is going to be that you choose a significance level, or the level or the size for the t-test, okay? Which is basically telling us, now this is important, this is telling us what is the probability of rejecting the null hypothesis. So we've made a guess. Remember what we've done with the null hypothesis. We've made a guess about what is the effect of xj on y. Or we can write it. What is the effect of xj on y? Okay, we've hypothesized what that is in the population. Okay, so in the third step, when we choose the significance level, we are choosing the probability of rejecting the null hypothesis when it is in fact true. Okay, and this is called a type 1 error. So a type 1 error, if the type 1 error is 5% or 0.05, this is basically saying that out of 100 times, we're going to make a mistake of rejecting the null hypothesis when it is true 5 times. Okay, so this is what it means. This is what the meaning of 5% is here. Okay, so we're making a mistake, or we are making a type 1 error. We are rejecting the null when it is in fact true 5 out of 100 times. Okay, so the fourth step, and we'll take some examples to understand this later, but this is basically the fourth step. We're basically saying let's choose a critical value so that we can apply a rejection rule. So when do we reject the null hypothesis? Okay, so the rule basically says you reject the null hypothesis when the t-statistic is greater than that critical value at whatever level of significance that you have chosen. So here, let's say we are thinking about 5%. So remember that under the null hypothesis, the t-statistic follows a t-distribution, and we can look at the t-tables to, once we know, so we can look at the t-tables, and what we need to know is a few things. So we need to know what our degrees of freedom are, what is the significance level of the test. So is it 5%, 10%, or 1%, right? So that, and then we can find what the critical value is looking at the test. And R can do this really very quickly, and we'll see that in the lab. So I'm going to show you a picture here of a one-tailed test, or a one-sided test. So this is a one-tailed test or a one-sided test. So here the probability density function is shown, and the critical value for the t-statistic is shown. So this is the critical value, 1.707. And this is basically saying, this is showing us what our rejection region is. So if our t-statistic was greater than 1.701, we would be in this region. Okay, we would be in this region right here, and we would reject the null hypothesis. Okay, and our null hypothesis was beta j is greater than or equal to 0, right? So this is going to be rejected when the t-statistic is greater than this value. This is what this is showing. Okay, and this is, we've conducted the test at 5%. Okay. But you can carry out the test at different significance levels. Okay, so at the 10% level or at the 1% level. Okay, so this is weaker, this is stronger. Okay, in terms of how often do you make a type 1 error. So this is saying if we are conducting the test at 10%, we are going to make the type 1 error 10 out of 100 times. This is saying we're going to make the type 1 error 1 out of 100 times. Okay, so this is always better than 10%, for example. But 5% is standard, and that's what's used. Okay, so you can look up the t-tables and you can see that these are the critical values. And if you were thinking about that distribution that we just saw, and we were looking at 1.701 as the critical value at 5%, the value for the 10% test is going to be to the left of it. Okay, so here, depending on our null hypothesis. And the value for the 1% test is going to be to the right of the 5% in this case. Right? So the rejection region is going to be smaller for the 1% test. Right? That's implied. So this is implied here that if we want to reduce the probability of a type 1 error, we must increase the critical value. That's what we saw in that diagram. Okay, so we get to reject the null less often. Okay, and it's also implied that if we reject at the 1% level, then we must also reject at 5% or 10% or any larger levels than 1%. But if we fail to reject at 10%, then we will fail to reject at any smaller level, 5% or 1%. Okay. So here we can see that for any large sample size, when degrees of freedom are greater than 120, we can use critical values from the standard normal distribution. So you don't look at the t-tables, but you can look at what the values are in the appropriate statistical tables for the standard normal. Okay, so for the degrees of freedom equal to infinity, right? So if you're looking at that column or that appropriate section of the table, then you're going to have these values, these critical values appear for the t-test. Okay, and these are for the one-tailed test. Okay, you don't have to remember this, R will tell you, but this is just for your information.